This is the second page of the Math 438 worksheet 4.1. Again, we are looking for critical points and extreme values of functions, sometimes on given intervals. Again, what we basically need to do is find the derivatives of these functions, find the value of the functions at the endpoints of the intervals, and also find the points or output values at any place where the function may not be differentiable. So here for number 4, we have a piecewise function, and so we're going to be looking for critical points for minimums and maximums of each of these two functions separately, as well as look at what's happening at that point where the two functions meet or perhaps form a discontinuity. So I've gone ahead and created a similar piecewise function, and I'm going to find the critical values of this one. So first I'm going to look at each of these functions separately and take the derivative to see if they have any critical values, and most importantly, whether or not that critical value even occurs in the part of the domain where that function is the one that's in effect. So I'm going to call this first function up here g. Then I take the derivative of that function, and then I set the derivative equal to 0. So I did get a 0 for the derivative at -3. Of course, I actually have to find the other coordinate, so I plug that -3 back into the function, and I got -23/2, which is -11.5. So that is an extreme value for the function, and because -3 is less than 2, then that is the function that is active. So this is an important point that we need to include in our critical values. Then I took a look at the second part of this function. I called that h. So I take the derivative of that, and it's -1/2, and -1/2 is never equal to 0. So this part of the function doesn't have a minimum or maximum within it because the derivative is never 0, but that makes sense because it's a linear function, and so, other than the endpoints, a linear function is not going to have a minimum or maximum. And then lastly, we do have to check the point where these functions possibly meet, see if it's a discontinuity, or see what's going on there. So what I did is I plugged 2 into both functions, and in both cases I got 1. So these functions do meet at the point 2, 1, and then I went ahead and I actually graphed it. It's not necessary to do it, but it helps to see what's going on. So you can see this is the point where the two functions meet, this 2, 1, and that's definitely a critical point. Then we also had the minimum of that function on the left. Turns out it is a minimum, so that's another important critical point. There were no critical points on this line, and this end's just going to keep going towards infinity. So the two critical points for this function is the minimum located at -3, -23/2, and the maximum, the point where the two functions within the piecewise function meet at 2, 1. So for number 5, we're asked to find the extreme values of this function on a given interval. And this function is interesting because this one has a hole, and the endpoint is actually the location of the hole. So we're going to take a look at that. Notice too, it doesn't ask for critical points, it asks for extreme values. So to me, that means it's asking not for points, but asking for the y values at those critical points. So again, I made my own function that's similar to that. I did a cubic function in the numerator and an x on the bottom, and I named an interval. So that 0 is not included because it's a hole, but I'm going to have the function go all the way up to it. and then I just picked another number. I took the derivative of the function. Now I could have factored out that x and canceled it out first, but I wanted to do the whole low d high minus high d low thing. And once I got that and simplified it all, I got negative 2x plus 6. Then, because I'm looking for extremes, I set that derivative equal to 0, looking for minimums and maximums. It happens to be equal to 0 when x is equal to 3. So I plug 3 in and back into the original function. Again, I could have canceled out that x, but I decided not to, just to be a purist about it. But it probably would have been easier to take that out. Regardless, I got 13. So the next part of this is actually really important too, because I have to look at the endpoints on our interval, right? So because I can't really plug in 0, I took the limit as x approaches 0, factored everything out, plugged 0 in, and I did get 4. So if that were a point, unfortunately it's a hole, but if it were a point, it would be at 0, 4. Then I took a look at the 5, and I plugged that into the original function. Again, I didn't factor out the x. I could have. In the end, I got 9. So in the end, I have 3 points. I've got this point at 313 that I got from that derivative and setting it equal to 0. I got this 5, 9, the end point on the interval that I chose, and this 0, 4, which is a hole. So my critical points are at 313 and 5, 9. I'm not really counting 0, 4 as a critical point because it's not really a point. But I will say that the extreme values of this function are 4 and 13 because the function does have a minimum of 4 on this interval, even though it's, approaching 4, and it definitely has that maximum at 13. All right, so last one for this page. Number 6 asks us again to find the extreme values, not points, just the output values, of a polynomial function on a given interval. So we're not going to have any problems with discontinuities on this. It's just going to be find the derivative, set it equal to 0, find the locations of those points, and then also plug in these endpoints of the interval, find out where they are, and compare it all and see which are the extremes. So once again, I made my own function to show you guys how to do this. Just a polynomial cubic function, and I created an interval that I knew would include some of these extremes. I took the derivative of that function, not a hard derivative at all, set the derivative equal to 0, factored it because the derivative is a second order function, just a quadratic equation, factored it, and I got zeros for the derivative at -2 and at 2/3. So I plugged in the -2 back into the original polynomial, and I got -11. Then I plugged in 2/3 into the original function, and I got -41 over 27, which is about -1.5. And then, so I've got 2 points that way, but I can't forget my endpoints. So with -3, I got -6, again plugging into the original function, not the derivative function. I plug in 1, and I got -2. I didn't have to graph all of this, but just to show you guys what's going on, I thought it was worthwhile. So I went ahead and graphed. I put all 4 of my points. I put both points that I got from the derivative being 0. The -2, -11 is a local minimum. The 2/3, -41 over 27 is a local maximum. And then I've got the endpoints on my interval, -3, -6, and 1, -2. So those 4 are the critical points. And then my minimum is this one here. And so the extreme value, because it's really just asking for the output, is negative 11. My maximum is at that point, and so my extreme value for that is the output value of negative 41 over 27. So that's a wrap on how to do the problems on the second page of worksheet 4.1. Again, mostly just looking for places where the derivatives of these functions are 0, looking at these endpoints, and looking at what the values are when there's any kind of point that's not differentiable for any reason.